Hello and welcome. It's time for section 12.2 on vectors. So, at this point I asked the class, what is a vector? And take a minute to shout out whatever you think they are. The usual answer is that they are something that has both a magnitude and a direction. And there are other definitions depending on whether you're a mathematician or an engineer or whatever else. But this is good enough for our purposes. A vector always has to have both a magnitude or a length and a direction. And this comes from Latin vecto, which meant to convey. So when you would imagine, if we draw the orbit of a planet, we have vectors based at the origin, the center, which is not the sun, but it's close to it. And the arrow shows where they are at different times, as though it were conveying them around in a circle or ellipse. So OA, OB, OC is a common way of writing them, where we have the base to the end point. Now, in print, it's usually written in boldface. When you write it by hand, they usually put an arrow over it. And so I am pretty strict about this one, that if you're doing a vector, I want to see the arrow over it, because it can get confusing if we have some things that are vectors and some that are scalars, just regular numbers. So whenever we see a vector, you are picturing an arrow where there's a base point and an end point, so it has both magnitude and direction. Now, the distance from the tail and the tip is called the magnitude, and it's written as absolute value of v. It's also called the length, or the norm, or the modulus, or the absolute value. There's lots of different names that all mean basically the same thing. I tend to say norm, so if I say norm, it's the exact same thing as magnitude. We say two vectors are equivalent if they have both the same magnitude and direction. You could also call this congruent, because this means you could drag and drop one on top of the other. So when we have vectors in space, a lot of times we would prefer them to start at the origin, but we don't have to. So what do I mean? Well, if I draw a vector like this, and I'll call it u, then any other vector that is in the same direction and the same magnitude is equivalent to u. Now, does that mean they're equal? Well, that's sort of a subjective term. They're not the exact same points in space. But equivalent is a math term that basically means they're the same in all the ways that matter. If I drew a vector over here, let's call it v, then another vector over here, v. These are all v. These are all equivalent to v. They are the same in all the ways that matter, because they have the same magnitude and the same direction. And yes, if you get out a ruler, these are probably not exactly the same length because I'm freehanding it, but let's assume they are. I am not going to get out a ruler and check that your figures are exactly the same. Yeah, if it's clear from context. Okay. So, we now say, well, what does it mean to add vectors? Well, the way I think of it as your traveling directions. Your first vector gives you a direction and a distance to walk. And then when you finish that, you start on the next one. So you can draw this using the tip-to-tail method. And this can also be called the triangle law or the parallelogram law. So let's say I want to draw what is u plus v here. U plus v. Well, I would draw one of these u's. So this is u. Then I would go to the end of it and draw a v starting from there. So this is v. Then u plus v is the net effect. It's saying, okay, so at the very beginning we were here. At the end, we're here. So u plus v is the shortest distance, the shortest path we could take to get from from point start to point end. I'm not using letters here, but from the beginning to the end. So this is u plus v. So you can see why I call it the triangle law, because it forms this triangle here. Alternatively, if we were to go the other way, if we were to do v first, and then u, we would get the same vector as the sum here. So this is v plus u. So not only does this show that why it's called the parallelogram law, because this thing makes a parallelogram, it also neatly shows us that vector addition is commutative. We can do it in either order. So if I had that's not a straight line. I had a vector A here, and I did a second vector B, A plus B. I'll just go over to the end of A. In fact, why don't I just drag and drop this thing? I will just grab this B, drag it over to start at the tip of A, and say, well, what is A plus B? Well, it is the straight line path from the point we started at to the point we ended at. So that's all there really is to vector addition graphically. You're just connecting the start point to the end point and going in the shortest distance. Okay. Scalar multiplication. Alright, now what is a scalar? Well, a scalar is an object with only magnitude, no direction. So it's just basically numbers. They form what's called a field, and you don't really need to get into the abstract algebra there. It is usually either the real numbers or the complex numbers, but in this class it's always the real numbers. So our scalars are always just real numbers. Now it's called this because you could scale up a vector. You could say, take this vector and multiply it by some scalar, and what that does is it keeps the same direction but changes the length. The only exception is the zero vector, because zero is just a point in space, really. It has no direction, or you could say it has every direction. So let's do these examples here. We're going to draw vectors A and B, and then we're going to get 2A, 3B, negative 3B, and 0A. So let's call this one A. Let's call this one B. Then 2A would be the same as A, but twice as long. In fact, if we could do this. We could do a copy, paste, and then get a second one and just attach them like this. This vector here is 2A. 3B, you could do the same thing, or you could just try and freehand it here. It'll be about like that, perhaps. Now, what would negative 3 be here? So what we're doing each time is we are multiplying the length by a number, but keeping the same direction. Well, if we multiply by a negative, that actually reverses the direction. And so it would end up like this. Negative 3b. So scalars are allowed to be negative. Multiplying by 1 simply changes the direction of your vector. It flips it 180 degrees. And 0a, you can't really draw it. I guess I would just represent it as a dot. would just be the 0 vector. There does have to be a 0 vector just for the mathematics to work out, but some would argue it's not really a vector because it doesn't have a direction, and it's a case. 0 tends to do weird things in math. It tends to be an exception to a lot of rules. We have to have a 0 vector even though it technically doesn't really seem like a vector at all. There's only one 0 vector. There's only one vector with length 0, and it's just 0. Alright. So, we can combine these things now. Let's do some of this. 2a plus 3b, a minus 3b, or negative 2a plus b. So, our rules, our order of operation from algebra still holds. We do multiplication before we do addition. So let's undo that. Get my base vectors back. 2a plus 3b. Okay, so we've got a 2a here. I'm just going to erase this. It'll be easier. Okay. So, we have 2a and we have 3b. It's hard to draw this just right. Because I'm the teacher, I try to be a little careful here, but I don't expect you all to draw them perfectly. 2a plus 3b then, well, we'll do our tip-to-tail method. We will take our 3b, we'll attach the end of 2a, and then 2a plus 3b will be the shortest distance from the beginning to the end. Or the shortest, not even distance, the shortest vector that connects them. Actually, I guess it's the only vector that connects them. Two a plus 3b. Alright, what would a minus 3b look like? Well, we have our a. Let's move it down here. I'm thinking ahead here because we have our a here. Then our negative 3b, let's just start from this tip. It'll go in the opposite direction of b. So sort of like this. Be 3 times the length of b. So I'd say it's about like this. This is a. This is negative 3b. So this is a minus 3b. How about negative 2a plus b? Well, we would get negative 2a would be a twice as long and in the opposite direction. And then b. So this, if I drew it as a straight line, this would be negative 2a plus b. You might be wondering about subtraction. And in algebra, the algebraists don't usually really even talk about subtraction. They usually think of it as addition in reverse. But I'm going to try to give an illustration of it anyway. If this is u, let's say, and this is v, then u minus v, we would draw an opposite v here. So this is negative v. So u minus v would be this. Now, another way to do this, though, would be by a tip-to-tip method, which is to say, if I draw U first, and then, I can never remember how exactly this one works. U, V, it's already here, I don't know. I guess what I'm trying to say is the shortcut is to say here's U, and here is V. U minus V is a vector in between them. Or this would be V minus U. Because if we went U and then V minus U, U plus V minus U would be V, which is the same thing here. So subtraction is tip to tip if you want to do it that way, but it's probably easier to just treat it as adding negatives. Okay. Now, there is another way of doing vectors, of thinking of them, and that's do it in component form. So let's say we have a vector that starts at a point x1, y1, z1 and ends at a point x2, y2, z2. The vector connecting PQ, we can get that by subtracting the endpoint from the start point in each coordinate. We can say, well, x goes from x1 to x2, so the distance in x is x2 minus x1. And for y, it's y2 minus y1. For z, it's z2 minus z1. And this works because the axes x, y, z are all orthogonal. Orthogonal means they're all at right angles. It's roughly the same thing as perpendicular. Perpendicular is Latin, orthogonal is Greek. Other than that, there's not really any difference, at least not in this class. And so we get sort of a duality here between points and vectors, which is to say, if we have a point in space, x1, y1, z1, we also have a vector that goes from the origin to that point, x1, y1, z1. They'll have the same coordinates. If it's a point, we use parentheses. If it's a vector, we use brackets. And so that's another thing where we want to be really careful about these. If you're talking about points, use parentheses. If you're talking about vectors, use brackets. They have the same components here. It's just that this, P, just represents a dot out in space. Here is P is x1, y1, z1. Whereas the origin over here, 0, 0, 0, or O, the vector then, x1, y1, z1, is the arrow connecting that origin to that point in space. So they're related, but they're not the same thing. So let's say we'll find the component form of the vector from 2, -3, 4 to b is -2, 1, 1. Well, we subtract. We say a, b, and we'll just subtract the second x minus the first x, which is -2 minus 2 would be -4. The y's would be 1 minus -3, so that's 4. Z would be 1 minus 4 is -3. So 4, 4, -3. And so that is the vector connecting A and B. Now it could also connect other points. We could shift it around in space, or we could move it to start the origin, and it would still be equivalent. But we're naming it after the points that we defined it with. All right, so let's keep going. What is length? Well, we know the distance formula, the Pythagorean theorem. So, if we have a vector that is ABC, we know that it is equivalent to a vector that starts at the origin and goes to point ABC. So we can just use the standard Pythagorean theorem to work out the length of that vector. So let's do some calculations here. So I'm not going to switch back to the slide, so copy this down. Here's A is 403, B is -215. Find the lengths of these two vectors, and then find these combinations, these linear combinations we call them. A plus B, A minus B, 3B, 2A plus 5B. Find these numerically. So we're not going to draw them, we're going to work out what they are in component form and find their lengths. Okay. A is 403. B is -215. So the length of A, well, we plug it into Pythagorean theorem here. 4 squared plus 0 squared plus 3 squared. This one is one that a lot of people just memorize because 16 plus 9 is square root of 25 is 5. 3, 4, 5 triangle is a common one that shows up. It's used so often just because everything comes out to whole numbers, and so that makes it easier to do the calculations by hand. Square each of these. -2 squared is 4. 1 squared is 1. 5 squared is 25. So we get square root of 30 is the length of B. Okay, what is A plus B? Well, we add these piece by piece. 4 plus -2 is 2. 0 plus 1 is 1. 3 plus 5 is 8. And then what is the length of A plus B? Well, it's square root 4 plus 1 plus 64 would be square root of 69. Yes. A minus B. So we say, okay, let's do A minus B. So let's go piece by piece. 4 minus -2 is 6. 0 minus 1 is -1. 3 minus 5 is -2. The length of A minus B is square root of 36 plus 1 plus 4 is root 41. Now, what is 3b? So how do we do scalar multiplication? Well, we want the direction to be the same, but we want it to be 3 times longer. Now, direction being the same means the relationship between the vectors will have to be the same. So, like the ratios. If you divided z by x, you'll get -5/2. So that should still be true when we make it 3 times longer. So what you do is you multiply each of the components by the scalar. So you distribute this guy in. We'll get -6, 3, 15. And then the length of 3b would be square root of 36 plus 9 plus 225. Which is, this is 45 plus 25 is square root of 270. Now we'll want to simplify this. So what's a perfect square goes into 270? Well, it would be 9. Square root of 9, square root of 30. And square root of 9 is 3, root 30. Well, look at that. That is 3 times the length of B. So, scalars can be pulled out when we're doing lengths. You cannot separate an addition. So, let me, in fact, we can see that right now. The length of A was 5. The length of B was root 30. 5 plus root 30 is not root 69. So, you cannot say length of A plus B is length of A plus length of B. That's not true. In fact, it's almost always less than or equal to, but usually less than. Very rarely it will be equal, but usually it's less than. But you can say that C times length of A is the same as the length of CA. Or C is a scalar, not a vector. We have not defined multiplying of vectors, and we're not going to do that today. Let's do one more. 2A plus 5B. Well, 2 times A would be 8, 0, 6. And 5 times B would be negative 10, 5, 25. So then add them together and we get negative 2, 5, 31. Then the length of 2A plus 5B would be square root of 4 plus 25 plus 961, which works out to square root of 990, or 3 times square root of 110. So it's just a lot of brute force calculation. The quiz on Monday will probably be something like this. Just calculate a sum of vectors and some lengths. Alright, so let's cover a few more things. So here are some properties of vectors. And they're all the things you would like. All the things that are true for real numbers. The associative property, if we regroup parentheses with addition, that's fine, doesn't change anything. If we add the zero vector to vector, we get the same thing we started with. There's an inverse. If you have a vector A and you add negative A, that gives you 0. These three together, these three properties combined are called being a group. If you ever take abstract algebra, you'll talk a lot about groups. Commutative. The order of addition doesn't matter. And there are two kinds of distributive properties here. If we put a scalar outside a sum of vectors, the scalar gets distributed into both of them. So C, A plus B, same as CA plus CB. This is like scaling up a whole triangle by C. If you were to draw an A plus B, then draw CA plus CB, it would be the same triangle, just C times bigger, or smaller. If, on the other hand, you add the scalars together, well, that also distributes. And that's saying if I, for instance, had a vector that was 2 miles and a vector that was 5 miles in the same direction, then together they make a vector that is 7 miles. 2, 5, 7. These last two properties, this is sort of a pseudo-associative property. If we have two scalars multiplied and then multiplied by vector, you can do them one at a time. And I say pseudo-associative, it's not real associative because these are not all the same thing. It's a mix of scalars and vectors, but it looks very similar to associative property. And if we have a vector times the scalar 1, we get the same vector. These last two, I think, are called being an algebra, like an algebra, but it's not really my field, so I don't really know that much about it. So, yeah, this slide is basically just telling you all the properties of algebra that work for real numbers also work for vectors. The only thing, again, we haven't talked about is how do you multiply vectors by each other, and that's for our next lecture. Alright, another thing we want to talk about is a basis, which is to say, when we want to have a few vectors that are the building blocks for all other vectors. And so, it turns out that we can always get by with just as many as the dimension of our space. So, if it's a 3D vector or 3D space, we need 3 vectors. If it's 2D space, we need 2 vectors. And we can always build everything else out of them. As long as they aren't redundant in some way. To really make sure we avoid that, we're going to insist they be orthogonal. They all be right angles. And they'll all be length 1, which is called being normalized. So, the easiest thing, the standard basis is these. I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. These are all length 1. They're all at right angles to each other. If we're in 2 dimensions, you would just drop the third component. I would be 1, 0, j would be 0, 1. And these little hats on them, just to indicate that they're special vectors. So let's take this. A is I plus 2j minus 3k. B is 4i plus 7k. Let's find 2a plus 3b. Now the reason this basis notation, this idea is really easy to use because it kind of treats the vectors as just like regular algebraic entities. That is to say, we've got 2, a is I plus 2j minus 3k, plus 3, 4i plus 7k. Well, we can go ahead and distribute this like we would with regular variables. 2i plus 4j minus 6k plus 12i plus 21k. J is missing, so if you needed to fill it in, you would write 0j. And so we would add like terms here. We would get 14i plus 4j plus 15k. Or if you prefer to write it as 14, 4, 15, that's fine. I am fine with either form. So, yeah, just a matter of treating them like regular algebraic entities. Now, we said a scalar is something that's magnitude with no direction. We sometimes want to have something that's direction but no magnitude. Well, we can't completely get rid of magnitude, but we will make it length 1, because 1, when we're doing multiplication, is a neutral element, so it won't affect our calculations if the length is 1. So we're going to show how to find these unit vectors, and the basic idea is, say, we're given a vector, we find its length and divide it out. So let's find a unit vector that's the same direction of A, which is 2i minus j minus 2k. So if A is 2i minus j minus 2k, then the length of A is square root of 4 plus 1 plus 4, which is square root of 9, or 3. So I'll say unit vector in the direction of A, and that's how I write it. I don't think anyone else does. You can just say U if you want, if it's clear what direction it is. Would be, well, we take A and we divide by 3. So I will multiply by 1/3 instead. It's 1/3 2i minus j minus 2k. And that's your answer. Let's get this 1/3 out front and this here. This is sometimes easy for calculations because it's all whole numbers. On the other hand, you might want to multiply it in. So if that's the case, you could write it as 2/3 I minus 2/3 j minus 2... Sorry, now it should be a 1/3 j minus 2/3 k. Or 2/3 negative 1/3 negative 2/3. And if you're not sure that you did this right, you would find the length of this and show that it is equal to 1. But you could actually just see it from here, because this is 1/3, and the length of this piece we already showed is 3. And we said that when we're finding length of vectors, we can just sort of pull the scalar out. So 1/3 times 3 is 1. So yeah, that's another thing that I might put on a quiz. Find a unit vector in a certain direction, because that's a pretty common thing we need to do. Okay, let's do one big example. This system, we're going to say it's in equilibrium, meaning it's not moving. So all the forces must zero out. There's no net force, means there's no acceleration. You know, that's Newton's law. force is mass times acceleration. So if there's no force, there's no acceleration, and vice versa. So there's a 100-pound weight here. And there's a string at a 50-degree angle and a second string at a 32-degree angle. Find out what forces these are. How do we do this? Well, let me copy the picture here. We've got a weight that is 100 pounds. And so we need to figure out what all the different vectors are. T1 is this way. And the way to do this would be to split it up into its components. See, T1 and T2 are not really in very convenient directions, so it would be easier if we could split them both up into an X part and a Y part. How do we do that? Well, let's look at this first piece. Let's do some trigonometry here. I've got a force here. Ugh. Here's T1, and we'll say length of T1 here. We're saying that's how long this side is. This is 50 degrees. And this is a right angle. So if we remember our trigonometry, we remember SOHCAHTOA. This piece here, cosine, let's call this T1x here. Cosine of 50 degrees would be adjacent T1x over hypotenuse, length of T1. So we could say T1x is the length of T1 times cosine 50 degrees. So I will go ahead and write that in there. Length T1 cosine 50. And then the y component would be length of T1 sine 50. And this is pretty common. Usually cosine is x and sine is y. That's just the way that we usually arrange things. It comes out that way. So then T2, let's see, how do we do this? Yeah, okay. So then T2x would be the length of T2 times cosine of 32 degrees. And T2y, and I'm not drawing the triangle this time, would be length of T2 sine 32 degrees. So what we need to say is that all the forces need to add up to 0. So we can say T1 is length of T1, we'll factor the length out, times, that's magnitude. The direction would be negative cosine 50 degrees, comma, sine 50 degrees. Now you may be asking why negative? Well, it's because the T1 is pointing left. So cosine of 50 would be a positive number. I want it to go to the left, so it needs to be negative. So for x, left is negative, right is positive. For y, down is negative, up is positive. And if you have a cosine and sine pair, that'll always be length 1 because the unit circle. T2, if we split it up, would be the length of T2 times cosine 32 degrees, sine 32 degrees. In this case, they're both positive because it's pointing both right and up. And there's one other vector here, and that is this one. I'll call it W for weight. W, it's not moving left or right, it's pulling straight down, so it'll be 0, comma, negative 100. So those are my 3 vectors. I'm going to erase the picture now. Take a picture if you need to. Because now that we've worked out the vectors, we know they add up to 0, so we should be able to treat this as a system of equations. So let's say t1 plus t2 plus w equals the 0 vector. So I'll go ahead and distribute these in now. Length of t1, negative, and cosine of 50 degrees, comma, length of t1, sine 50 degrees, plus length of t2, cosine 32 degrees, length of t2, sine 32 degrees, plus 0, negative 100 equals 0, 0. So now we've got to do some algebra. So we will pick one or the other to do first. I'm going to say x because it only has 2 components. It doesn't have this 100 in it. So the x here would be t1 cosine 50, I'll say negative t1 cosine 50 plus t2 cosine 32 is 0. So we could solve this. We would say, well, then t1, length of t1 is length of t2 cosine 32 over cosine 50. So this, we can now eliminate t1, plug it in to the other equation. So the y equation would be t1 sine 50 plus t2, length of t2, sine 32 plus negative 100 is 0, so I'll just call that equals 100, save us a step. And then we can plug this in right here. So I'm going to erase this red line. So if I plug that in, I would get, let's see, how do we do this? Where are we? All right, so I would get t2 cosine 32 degrees sine 50 degrees over cosine 50 degrees. Yeah, that's right. Plus length of t2 sine of 32 degrees equals 100. And now at this point it's a calculator problem. If this were something that's on a test, I would stop here. If you get to a point where you would need to pull out a calculator, just say, this is as far as I can go without a calculator. Alright, so I'm going to pull out my calculator, make sure it's in degree mode. And I'm going to go an estimate. Cosine 32, sine 50, divided by cosine 50, gives me 1.01, yeah, 1.01 length of t2 plus sine of 32 is 0.53 sine of 32 is 100. Erase this line here. So that means, or wait, no, sorry, that's not sine of 32. Sorry. Length of t2 is what I meant to say there. So 1.54 length of t2 is 100. So 100 divided by 1.54 is 64.9. And then length of T1 would be, let's plug it into this, 64.9 cosine of 32 degrees over cosine 50 degrees. Sine 32 divide by cosine 50 gives me 85.7. I guess technically these should be approximate signs, but okay, so those are our lengths. Now we just have to plug them back in to the formula then, to our equation. So T1 we said, and this takes more than just one screen. I've had to erase a lot, but yeah, T1 would be the length of T1. So it's 85.7 times negative cosine 50 sine 50, which we should really work out what that is, I think, in my opinion. 5.7, so this would be negative 55.1 and sine of 50 times 85.7 would be 65.7. That's T1. T2 would be, plug it back into format, length of T2 is, what did we say it is? 64.9. So 64.9 times cosine of 32. And the other one, and the y is times sine of 32, so would be 55.0 34.4. So if we add these together, T1 plus T2, there's a little rounding error here. You can see these are not exactly 0, but it's come out to almost exactly 0, 100. Little rounding errors happen, but this works because that means T1, T2 are having a net force of up by 100, which exactly cancels out the weight, which is down by 100. Okay, thank you. And email me if you have any questions.